So because the Fibonacci sequence doesn't have a traditional or an explicit equation, we don't want to say, though it's a crap sequence, it doesn't have any equations at all. We want to write an equation that adjusts itself. The two types of equations that we had are simply too restrictive because the Fibonacci sequence doesn't fit either of these molds. It's not arithmetic because it doesn't have a straight up adder. It's not geometric because it doesn't have any sort of multiplier. So we're too limited by these equations to work with the Fibonacci sequence. And that's why we have to use a third option. The third option, which we've never seen before, and this is brand new to us now, is called a recursive definition. So it's not an arithmetic formula, it's not a geometric formula. A recursive definition is a little bit different looking. And you'll see the recursive definition over here on the right-hand side of the problem. Now, to translate it, I want to make sure that we understand what we're seeing, because the first thing you probably noticed about this thing is that it's not just one equation. This recursive definition has three parts to it. So I'll translate each part. The first part says t of 0 equals 0. What that really means is that the 0 term, sometimes we call that the initial value, the 0 term is 0. The second little factoid says that t of 1 equals 1. That means the first term is 1. And if you're looking back to the table, hopefully that makes sense. The 0 term was 0. The first term is 1. They could have given us more information. They could have said t of 2 equals 1, because the second term is 1. They could have said t of 3 equals 2, because the third term is 2. They could have said t of 4 equals 3, because the fourth term is 3. They could have said lots of different things. They just happened to tell us the first couple of numbers in the table that we saw. So they translated the table for us, basically. But the third part is where it gets interesting. It says t of n equals t of n minus 1 plus t of n minus 2. And that might be the part where you're going, wait, what? What is that? So I think the best way to understand this third part, this equation-looking part that looks quite confusing, is to actually use some real numbers. Take a look at the first part to the question underneath that says, use the recursive definition to prove that t of 6 equals 8. Those are real numbers. So let's use those real numbers. Notice how it says t of 6. I'm going to highlight that 6 because the formula says t of n. So I'm going to make a quick assumption here. It looks like that the 6 is where the n was. So I'm going to make that quick assumption for a moment, and I'm going to assume that if I put a 6 wherever the letter n is, that maybe I can make sense of this thing. So I'm going to take this formula looking thing, which I've never seen before, and I'm going to put 6's where all the n's are, because that's what they gave me, so that's what I'm going to use. So I have t of 6 equals, and then I'm going to copy out this equation. T of, instead of n, 6 minus 1, plus t of, instead of 6, or instead of n, 6 minus 2. So notice I replaced all the n's with 6's. You can see my little substitutions there that I highlighted pink. Now, let's see what this looks like. I've kind of written too big in the box there, so I'm going to give myself a bit of scratch space. We have t of 6 equals t of, now in this parentheses, 6 minus 1. It seems silly to write 6 minus 1. We know what that is. 6 minus 1 is 5. Plus t of 6 minus 2, again, seems silly to write. 6 minus 2 is just 4. But now I'm going to look at this and ask myself, well, what does that mean? T of 6 equals t of 5 plus t of 4. Remember how t refers to wherever you are in the sequence? So t of 6 is this value here. T of 6 is t, so I'm going to the t row in the table. Where the 6 is, that would be an 8. So I'm going to put an 8 here to show t of 6 is 8. The 6th term is 8. Then where it says t of 5, that's the 5th term. So if I go to where t is 5, that's this value here, so that's the 5, plus T of 4, well, that's the fourth term. If I look at my table, T of 4 is 3. And now I want to look at what I wrote. 8 equals 5 plus 3. Oh, yeah. 8 is equal to 5 plus 3. That makes total sense. So we did prove that the equation works. It's weird because we still don't know why the equation looks the way it does, but the equation does work. So take a second to think on that for a moment. Does that make sense? Do we see where these numbers came from? Do we see why the equation works? Because if it works, it seems as though we figured out something really logical. And hopefully you can follow my logic in the following way. Remember where we wrote T of 6 equals T of 5 plus T of 4? What we were really saying when we said T of 6 is that we were talking about the sixth term. So if I translate this logically, T of 6 means sixth term, T of 5 means fifth term, and T of 4 means fourth term. And if I translate this equation, notice it says T of 6 equals T of 5 plus T of 4. Notice how that looks if I translate it into more words here. The sixth term is equal to the fifth term plus the fourth term. That's totally true. The sixth term in the table was equal to the fifth term plus the fourth term. That was what the Fibonacci sequence is all about. To get the next term, we had to add the two numbers that came before it. 3 plus 5 is 8. And that's why it worked, is to get the sixth term, we were just focusing on the two terms that came before the sixth, the fifth and the fourth. And it seems like this formula is actually just saying what we already knew. They said it in a fancy way, but that's what this formula is actually saying, that to get the sixth term, we just needed to take the fifth and the fourth. The term that came before it and the term that came before that. So see if that makes sense. And if it does, try to answer question number 2. See if it makes sense to talk about the 8th term in the sequence. If you're not sure, the next video should clarify.